The James Webb Space Telescope has once again pushed the boundaries of what we know. It has discovered a galaxy so ancient and unusual that it's challenging long-held assumptions about the early universe. To grasp the significance of this, we need to go back, not to the beginning of time, but to the year 2022. Until then, the most distant galaxy ever observed was GNZ 11, discovered by the Hubble Space Telescope. This was a major milestone. Hubble, with its 2.4-meter mirror and impressive optics, had already taken us deep into the cosmos. But even Hubble had its limits. Then came the James Webb Space Telescope, or JWST, equipped with a massive 6.5-meter mirror and tuned specifically to capture infrared light, the stretched ancient light emitted by early galaxies. JWST didn't just continue Hubble's legacy, it shattered its records. In one of its early observation campaigns, JWST identified a galaxy named JD's GS-Z13-0, holding the record for the farthest confirmed galaxy at that time with a redshift of 14.32. Redshift measures how much light from a galaxy has been stretched by the expansion of the universe. The higher the redshift, the older the light. But then another galaxy appeared, named MAMZ14, with a redshift of 14.44, pushing our view even further into the past. What stunned scientists wasn't just how far away MAMZ14 was, it was what the galaxy looked like. It's incredibly small, roughly 500 light-years across, which is tiny compared to the Milky Way's sprawling 100,000 light-year width. Despite its size, it's astonishingly bright. Galaxies that formed this early in the universe were expected to be faint and difficult to detect, but MAMZ14 is radiating with the intense light of newly forming stars, a rapid-fire stellar nursery from the universe's earliest epochs. And yet, something was missing. There was no sign of a supermassive black hole. Typically, galaxies undergoing intense star formation also contain a supermassive black hole at their core. These black holes are thought to play a crucial role in regulating star formation and influencing galactic growth. But in this case, MAMZ14 appears to be an exception. The surprises didn't end there. Using a spectrograph, JWST analyzed the galaxy's light and found it rich in nitrogen, much richer than expected. This chemical fingerprint is similar to what we observe in some of the oldest star clusters surrounding the Milky Way. It suggests that MAMZ14 is forming stars in environments far denser than we anticipated. More importantly, it means that multiple generations of stars may have already lived and died by the time MAMZ14 formed. This challenges the idea that early galaxies were chemically simple, composed mostly of hydrogen and helium. Instead, it indicates that galaxy formation may have begun much earlier than current models suggest. This raises an important question. How many galaxies like MAMZ14 are out there? Before JWST, it was assumed that such ancient galaxies would be incredibly rare, but now they're being found more frequently than anyone expected. These bright, compact objects, sometimes referred to as little red dots, are showing up all across JWST's sky surveys. While MAMZ14 may currently hold the record, it may soon be surpassed. What makes this moment so exciting is the sheer volume of new data pouring in. Each discovery challenges our previous assumptions. If early galaxies were more common, formed stars faster, and were more chemically advanced than expected, what else might we be overlooking? Galaxies like MAMZ14 don't just surprise us, they point out the gaps in our models. Current theories of galaxy formation suggest early galaxies should be rare, slow-growing, and chemically simple. MAMZ14 is none of these things. It's fast, bright, and chemically complex. That doesn't mean our models are wrong, but they are clearly incomplete. The implications are profound. This could mean the early universe was far more dynamic and structured than we ever imagined, and this is only the beginning. Soon, the Nancy Grace Roman Space Telescope will join JWST in scanning the cosmos. With its wide field of view, Roman will be able to survey much larger portions of the sky in great detail. Together, these instruments could reveal hundreds, maybe even thousands, of galaxies like MAMZ14. Each one will serve as a time capsule from a period we are only just beginning to understand. For now, MAMZ-14 stands as a milestone, a beacon from a time when the universe was still taking shape. But the deeper we look with JWST, the more the universe surprises us. Some scientists have gone even further, suggesting that our entire universe might exist inside a black hole. A recent study has uncovered a puzzling observation. Most galaxies seem to rotate in the same direction. This is significant because in a truly random universe, galactic spins should be evenly split between two directions. But the data shows a preference, contradicting current cosmological expectations. This unusual alignment has led some to consider bold alternatives. In physics, when matter collapses into a black hole, it creates an event horizon, a boundary beyond which nothing, not even light, can escape. What happens beyond that boundary remains a mystery. One hypothesis, known as black hole cosmology or Schwarzschild cosmology, suggests that our universe could be the interior of such a black hole, formed within a larger parent universe. This idea ties intriguingly into the Big Bang. According to standard cosmology, the universe began as a singularity, a point of infinite density, much like the center of a black hole. If our universe originated inside a black hole, then the Big Bang wasn't an explosion in space, but rather the birth of a new universe inside a collapsed star from another reality. This theory opens up another fascinating possibility. Every black hole in our universe could potentially be the gateway to a new universe. If true, this might help explain why the physical constants of our universe appear finely tuned for life. Universes born inside black holes that are stable and capable of sustaining structure might be the ones that endure. There's also the concept of torsion in extended versions of general relativity, such as Einstein-Cartan theory. Torsion accounts for the intrinsic spin of particles and could alter the curvature of spacetime. Some versions of this theory suggest that at extremely high densities, torsion might create a repulsive force. This could prevent the formation of singularities entirely. Instead of collapsing into an infinitely small point, a black hole's core might undergo a big bounce, rebounding and expanding outward, potentially giving rise to a new universe. This rebound could be what we interpret as the Big Bang. If this theory holds true, it would fundamentally alter our view of cosmic origins, suggesting a self-replicating cycle of universes. Supporting this idea is evidence that the universe may have a preferred axis. Large-scale cosmic structures show a certain alignment in how galaxies are distributed and move, contradicting the assumption that the universe should be homogeneous and isotropic on the largest scales. This anisotropy might reflect unknown physics, or hint at how our universe formed, possibly inside a black hole. Furthermore, the discovery of massive ancient galaxies so soon after the Big Bang continues to puzzle astronomers. While the black hole universe theory is compelling, there might also be more grounded explanations. Some of the measurements used in our cosmic models, such as the rotation speed of the Milky Way, could be off. Regardless of the cause, what's becoming clear is that the universe is far stranger than we once thought. The surprising patterns in galaxy rotation and the unexpected complexity of early galaxies are forcing scientists to re-examine long-standing ideas. As our tools become more powerful and our observations more detailed, our understanding of the universe continues to evolve in fascinating and unexpected ways.